Hello everyone and welcome to the Dipy workshop. I'm Bramsh Qamar Chandio and in this lecture we will discuss tractometry and bundle analytics. Tractometry is a set of methods to study tract-specific microstructural changes across groups and subjects. DTI measures such as fractional anisotropy, mean diffusivity are projected along the length of the tracts to create bundle profiles. Bundle profiles of subjects and groups are compared to find any anatomical differences along the length of the tracts. Most common approach of tractometry is given a bundle, a co-representative streamline is created, and then the anatomical measures such as fractional anisotropy are projected along the length of the co-representative streamline. As shown in this plot, on the x-axis we have length along the tract, would be the location along the streamline, and on the y-axis we have fractional anisotropy measure. Here we can see bundle profiles of two groups, control and patient. We can visually see that around 80 to 100 location there is a huge difference between the bundle profiles of two groups. This could also be done for two subjects to find any differences between those two subjects. This is a summary of tractometry. This session will be more focused around bundle analytics, a computational framework for investigating the shapes and profiles of brain pathways across populations. Bundle analytics, or as we call it BUAN, is a framework to study group differences in white matter tracts at specific locations. BUAN has four important steps: bundle extraction, bundle profile creation, and then the statistical analysis of bundle profiles. Fourth one, bundle shape analysis, or which could also be used as bundle quality assurance. The results are shown on Parkinson's data. BUAN is publicly available in Dipy. Some of the use cases of BUAN include finding group differences in white matter tracts at specific locations due to any neurological conditions, or studying any effects of medications, post-surgery validation, comparisons between any groups, or just studying brain pathways. In earlier sessions, you learned about how to create tractograms by using tractography algorithms. Diffusionmri is given to the tractography algorithms and it generates whole brain tractograms, which gives us the digital representation of white matter pathways. However, tractography data is unordered and unstructured, densely populated, creating up to 1 or 2 million streamlines, which becomes very difficult to inspect visually and computationally. It also creates a lot of false positives. Let's look at this example of simulated streamlines from streamline 1 to 5 streamlines here. This is an example showing how unstructured and unordered tractography data is. As we can see here, the streamline 1 is starting at a different location as compared to the rest of the streamlines 2, 3, and 4. And in this example, the streamline 5 ends very earlier as compared to other streamlines. And each streamline could have different number of points. Another important thing to note here is the way this data is saved. We don't know from where it is starting. For example, here on the right we can see, let's look at the streamline 1. It has 10 points, and in this example it is starting from A. Let's say this is the A point. This is the first point saved in our data, and then this is the B point, and C, and so on up to J. If it is saved in this way, when you visualize it, it will look like this. And the interesting thing to note here is, even if it is flipped in a way that the first point becomes this one, as it is saved like here, J becomes the first point, I becomes the second point. and A becomes the last point. This is called flipped streamline. This problem is called unordered streamline problem. And another problem that I was talking about tractography data is it's densely populated. So we are interested in looking at specific pathways, specific streamlines that are located at a specific location in our brain. From anatomy and literature, we know that there are almost 100 different white matter tracts that are located at a specific location in the brain, and they also have a specific function associated with them. For example, if we look at this figure, we can see here corticospinal tract, which is involved in the movement, and then we see optic radiation, which transmits the input from retina of eye to the visual cortex. So to solve this problem, one of the important thing to do is to extract specific white matter tracts from the whole brain tractogram. This is an overview of how bundle extraction happens in BUAN. We will look at this closely. First, we want to register all of the input tractograms from different subjects to common space. Because data comes from different scanners and each subject has a different coordinates, it's in a different coordinate system, each subject has its own native space. But when we want to do group analysis, we want all of the subjects to be in the same space so that the specific location in the brain corresponds to the same location across all the subjects. To do so, we do streamline-based linear registration. We register all the input tractograms to the model atlas or common space. Here it is MNI space. After we have registered all the input data into common space, now we start doing bundle extraction. In the previous session, you already learned about reco bundles and how it works. In BUAN, we presented auto-calibrated reco bundles. Let's see how it is different than reco bundle. So reco bundle takes a tractogram, which is now in the MNI space, and a model bundle, and it extracts the bundle that looks like model bundle in our input data. We added another step. After we have extracted this bundle, we do the refinement step where we give the input tractogram again, and now this extracted bundle becomes a new model bundle. Before we had a model bundle coming from the atlas, but now the model bundle is one that is extracted from the data itself. This serves as a self-supervision step, and then we perform reco bundle again with this new inputs. And this is the output that we get, which is very much refined, and it has an influence from the data itself. I'll stop it here, and in the next part I will talk about bundle profile creation.